All right, so a few things. First, before we get started with today's topic, I often talk about jobs and the optics industry, and obviously the economy is changing quite a bit. Tomorrow night, there's going to be an online meeting of the Optical Society of Southern California. You can join it via Zoom. And I'm sure we're going to hear all sorts of things about the local optics industry. I can't promise anyone that the job outlook is great right now. On the other hand, I think we're also going to discover that there are probably some sectors doing surprisingly well, some niche areas in which there actually are a ton of orders. So let's talk about that a little bit. If I were on the job market right now, one of the first things I'd be doing is going through public records to find out which companies have contracts with the CDC, which companies have contracts with the county and state departments of public health, because I guarantee you those businesses are not going to be hurting. And not just now, this thing is going to come and go in waves. In 1918, the flu actually went through a few waves because first a whole bunch of people get it, then the survivors are immune, so the disease doesn't propagate for a while, but then it builds up in some areas where people are not immune, and then it spreads back from there to whoever else is still not immune in areas that got hit before. So we're going to see a few waves of that, and state and county and federal public health agencies are going to be busy. I'd be looking at any companies that sell supplies to hospitals, not just because of COVID-19 patients, but in a couple months, they're going to have to relax some of these restrictions. And all of those elective procedures that were put off right now, those are going to be done. And so there's going to be a huge backlog. All of those colonoscopies that were temporarily delayed, all of those diagnostic tests that were temporarily delayed, all of those scans that never got done, all of those elective procedures, all of those frankly necessary procedures that they put off just because the risk of getting COVID-19 while recovering from the procedure was not worth the benefit of the procedure, those are going to be done. Any company that's making software for working from home, whether it's Zoom or WebEx or whoever, they're going to be hiring. I have a friend who works for a company that basically does security software for corporate clients, and he's working around the clock right now because everybody is expanding their online operations. So however much business he had before the outbreak, now it's even better. So think about things like that. If you have any interest in education, if you've been a learning assistant, if you think you might want to be a teacher, all of the major textbook publishers and even the minor textbook publishers have online homework divisions. I don't know what you think of online homework. I don't know what you think of Blackboard. Maybe you love it, maybe you hate it. Either way, anybody who makes online teaching tools is rolling in cash right now. Those people will be hiring. They'll be hiring sales reps. They'll be hiring programmers. They'll be hiring content specialists. They'll be hiring anybody with a pulse who can work a help desk. They'll be hiring in every role imaginable. Now, obviously, as physics majors, you want to get a technical role, but if all you can do is get your foot in the door during what is going to be a very severe recession, it could be a very short-lived one. There's a ton of backlog demand. I'm not convinced that this will be a long-term recession, but I could be wrong. Either way, anything that gets your foot in the door could be huge. If all you do is get yourself a job on the loading dock at a company that makes surgical masks, and then something opens up in their R&D division, do not underestimate the power of having a manager who works for the company that can say, yes, this is a person who will show up on time and not cause trouble. Obviously, you wouldn't get an R&D job solely because you were the best guy on the loading dock, but if you have a good transcript and a technical reference, and someone inside the company can say, yeah, this guy shows up on time and doesn't cause trouble, that's huge. So think about these things. Think about who's actually making money right now. And I mean, even a company like Uber Eats or Grubhub, these companies have big behind the scenes technical divisions. Uber is a tech company in that their entire platform is based on apps. It's based on data analysis. So there's a whole bunch of behind the scenes people doing what they call data science, statistics, and programming. If you get an entry-level job at one of those companies, if all you do is get some entry-level help desk position at Pearson, and then something opens up that requires some actual real technical expertise in how to do some programming and physics to make simulations for their online homework system, hey, you've got a reference who can say that you show up. So think about things like that. Any questions about that? I mean, as of a couple months ago, I thought for sure that this would be a very different economy you're graduating into, but these are some things to think about. I'll make it a little more tangible. I have a cousin who's about your age. I'm from a very, very big family. I have cousins who are almost old enough to be my parents and cousins who are young enough to be my kids. And one thing I pointed out to her is that while Wisconsin isn't exactly going to do great, Kimberly-Clark, a major manufacturer of paper products, including a lot of hospital supplies, is headquartered in Wisconsin. And a company formerly known as Sigma Aldrich, now I think Millipore Sigma, they got acquired. They make supplies for biology research labs. They have a major facility in Milwaukee. Those would be great jobs. And even if all she gets initially is a job packing boxes at Sigma Aldrich, well, she's going to have a biology degree. If something opens up in one of their biology labs, that will help. Okay, on a different note, starting Thursday, instead of using Zmax, we're going to be using a Python program that I wrote. And so there are many Python development environments to work in. I particularly like this one called Spider. It's part of the Anaconda package. And the main reason I love Spider is the same reason I loved Canopy, which is that I spent several years as a MATLAB user. And I kind of got used to the MATLAB environment where you've got a command line, you've got an editor, and then you've got various windows for browsing your variables and looking at your plots. It looks and feels like MATLAB. And the look and feel of a comfortable interface is not something to be overlooked. But whatever you choose to use, get some kind of Python development environment working on your machine by Thursday. Spider is free. There are lots of free Python development environments. Get one of them working because we will start using that on Thursday. Any questions on Python? Just remember, we won't actually, I'm not going to have you do any programming in Python. You're not going to have to rewrite any code. You're going to take code that I wrote and you're going to change the value of some variables in it. But the reason why we're doing that is I'm not a GUI programmer. I don't know how to make nice graphical user interfaces. I've never had the patience for it. This kind of code for modeling thin films is just easy enough that you can write it yourself and not be able to justify the expense of a commercial package. What you're really paying for with a commercial package is the graphical user interface. But the one thing you get from using a commercial package, the one thing you get from using the non-commercial package is that you actually see the variables laid out quite explicitly. I mean, I'll show you right now what we're going to be doing. This is the code, and you're going to be modifying just a small part of it. You're going to be modifying some true-false variables telling you what you should or shouldn't plot. You're going to be switching between execution modes for the output. So there's a variable that goes from 0 to 5 that specifies what kind of output to use, output to display, excuse me. There'll be a variable for a wavelength and angle, some refractive indices, and then finally a bunch of variables for layer thicknesses and refractive indices. And so you're just going to be changing those. You're not going to have to figure out the logic of how Python handles lists versus arrays versus whatever. So try to get that by Thursday, and this code is posted on Blackboard. All right. Now we are going to switch to today's topic. And I apologize for the meme on the desktop. All right. Oh, wait, we did not quite finish the last lecture. So let's go back to those slides. Okay, so finish up some stuff with diffraction by circular apertures. All right, so we were talking about the way that light spreads out when it travels through a circular aperture. Now, it turns out that we were initially doing lenses, and we were just assuming that we have something at the focal point, and then the light goes in straight lines. Well, the rays would go through in straight lines if light were just a ray, but instead it spreads out a little bit. But the situation we were modeling turns out to be relevant even to light that gets focused, because of course, light that gets focused, whether it came from infinity and went to the focal point or came from a finite distance and went to some other finite distance, light that gets focused doesn't stay focused. Light comes to whatever point the image is going to format, and then it keeps going. And at that, of course, it spreads out a little bit like a wave. It's always spread out beyond where ray theory would predict. But it still has a minimum diameter here, which means that right here, all of the light is traveling horizontally. For this brief moment, this little region of space, the passage of the light waves, not the rays, the waves, is purely horizontal. And then the beam starts expanding again, which means that right where it's horizontal, we could treat that as being an aperture, all right? We've got a surface where the phase is the same everywhere along here, and whatever that beam width is, that would be our aperture diameter. Then it's going to spread out at an angle given by sine theta equals 1.2 lambda over the diameter. So let's talk a little bit more about using that concept to understand beam profiles. This would be an ideal intensity profile. 0 outside of the beam, 1 inside the beam. Of course, in reality, it's spread out. And there are many different ways that people measure the width of this peak. And this is not just a point about optics. When people measure peaks in any area of physics, because you're always looking at a signal that has a peak. You're looking to see where is the signal that you're detecting, whether it's a light intensity, a current, the resonance of something vibrating, whatever it is, there's always some kind of peak. Some people measure the width as what they call the full width at half max, the distance from here to here, where these 2 points have half of the maximum value. And that's just very convenient in the lab. It's very easy to look at something and say, what's the peak? What's half of the peak? Other people prefer to use 1 over e squared as the width. And the reason they use 1 over e squared is that it's common to write Gaussian curves in this form, e to the minus 1/2 distance from the center squared over width squared. In statistics, that width is called sigma. It's called other things in other fields. And if you're 2 sigma away, if r is 2 sigma, then we've got 4 sigma squared up top divided by sigma squared and 2. So we've got e to the minus 2. But calculating 1 over e squared multiplied by the peak off the top of your head in the lab is not as easy as dividing by 2 usually. So people tend not to use that quite as much as full width at half max. But the key thing is that all of these different measures of beam width are generally within a factor of 2 from each other. So if you need something very precise, and I know a student who is or was before the recession interning at a company where they spent all day doing very, very careful measurements of beam width for some very high precision calibrations. But even then, they start off with a more casual definition. They have to figure out, okay, do we need something that can measure a couple millimeters across? Do we need something that can measure 10 or 20 microns across? And all of these definitions are within roughly a factor of 2 of each other. All right. So if we look at this, this surface is almost, well, it's roughly hyperbolic, all right, in that there are these asymptotes. If we're very far from the focus, very far from where the beam width is so tiny that we have to take the wavelength of light into account, if we're very far from the focus, we can use geometrical optics as an approximation. And in geometrical optics, everything goes in a straight line. So these asymptotes are going to be approximately the angle that the beam is spread over when you're far from the focus. And a curve that goes towards the asymptotes can be approximated with a hyperbola. The actual beams aren't exactly hyperbolic, but it's a very, very good approximation. So if W is the width, it's the distance from the axis, and Z is the distance from focus, well, W is going to depend on Z. The further we are from focus, the bigger the width is. So W squared over W min squared minus Z squared over Z naught squared is 1, where W min is just the width when Z is 0. If we block this out, so Z is 0, we'd have W squared over W min squared is 1. And this is the standard form for of the equation for a hyperbola that you probably learned at some point in algebra or trig. And oftentimes, W min would be approximately 0.6 lambda over sine theta. Now, I haven't said yet what Z naught is, but let's think this through. So W squared over W min squared is Z squared over Z naught squared plus 1. And if Z is very large, then Z squared over Z naught squared will be way bigger than 1. We could leave off this 1. I mean, if we were 1,000, if the beam width were 1,000 times its minimum width, you know, it's spread out quite a bit, well, 1,000,000 is not that different. 1,000 squared would be 1,000,000, and 1,000,000 is not that different from 1,000,001. So we would get that W min over Z naught times Z is Z tan theta, okay? Because W over W min equals Z over Z naught, and W over Z has to be tan theta when we're far away. Because when we're far away, here's theta, distance from the axis will be W, distance horizontally will be Z, so W over Z is tan theta. So tan theta is W min over Z naught, or Z naught is W min over tan theta. Okay, but what is Z naught? Well, let's just plug in here. W over W min is square root of 1 plus Z squared over Z naught squared. Let's say that Z were equal to Z naught. We're trying to figure out what this Z naught is, so let's just say, okay, what if we're that far away from focus? Well, then we get that W over W min is square root of 2, or 1.4. So Z naught is often called the depth of focus. It's how far you have to go from the focus before the beam width has changed by about 40%. You might say, well, why measure it by seeing when it's changed by 40% instead of something else? Well, it's a convenient measure. Any questions so far? Okay, so this Gaussian approximation, besides being accurate, besides the fact that last time I showed you a plot of the Airy function and the Gaussian function, and I noted that they basically sit on top of each other, they're almost the same. The Gaussian is much easier to work with. So let's calculate the power. The power passing through a surface will be the integral of I dA. All right, so we're going to have I max of Z. And you might be thinking, why does the maximum intensity depend on Z? Well, here the power is spread out over a very small area. Here it's spread out over a large area. So if I fix the value of Z and I just ask, when I'm this distance from focus, what's the maximum intensity? The maximum intensity will be right here on axis. If I go over here, the maximum intensity will be larger. But keep in mind, that's the maximum at a distance Z. The overall maximum is right at this point here. So if I ask what's the maximum value looking everywhere in space, it's unique. But if I ask what's the maximum value just in a plane, a distance Z away from focus, well, that depends on Z. Okay, so we've got some maximum intensity as a function of Z, and we've got this Gaussian, e to the minus r squared over w squared, and w squared depends on Z. And we're integrating over the area, we're integrating over a plane, and since our integrand is a function of r, it's much easier to work in polar coordinates. So that's what we're going to do. We're going to have r e to the minus 1/2 r squared d phi dr, because the area element is r dr d phi. When we integrate over phi, I don't see a phi anywhere in this integrand. So the integral of d phi from 0 to 2 pi is just 2 pi. We could do a u substitution here, and we're going to get that the power is 2 pi I max w squared. So I max is equal to the power over 2 times pi w squared. So a convenient way to think about it would be, pretend initially that w was the true width. Well, it's not actually the true width, of course, because some of the power is spread out beyond w. So if we pretended that the area was like 2 circles, twice that of a circle with radius w, then the power, we could think of the power as being spread out over 2 circles, each with radius w, and that would be a sort of convenient measure of the power here. That would be a convenient way of thinking about the peak intensity. That the peak intensity is what you would get if you took all that power and spread it out evenly over 2 circles, each with radius w. Questions? All right, so what I want you to take away from that is that this model of that this idea of diffraction by a circle provides a convenient way for understanding beams. And you can actually go much further into the theory of Gaussian beams. Any textbook on lasers will have a good section on the optics of Gaussian beams, but you can get pretty far in understanding a Gaussian beam just by thinking about diffraction, just by thinking about the fact that the minimum spot size will be roughly 0.6 lambda over sine theta, and then it'll spread out, and as you get farther away from focus, follow these asymptotes, and with a very simple model, you can get reasonably good predictions. Okay, let's switch topics a little bit. Let's talk more about this and talk about what diffraction does to image resolution. So we established that if we have a point object, the image is not a point, but rather something spread out and wavy. Now, if we put 2 things too close together, then the images might partially or mostly or fully overlap. So here we've got 2 point objects that are pretty far apart. And we can see there are 2 peaks. Now remember that because this is above the axis in the object plane, it's below the axis in the image plane. And okay, so their peaks don't overlap, their tails overlap a little bit, but we can tell them apart because the spacing between the objects is larger than 0.6 lambda over the numerical aperture times the magnification. And remember that magnification comes in because in the image plane, the distance is just 0.6 lambda over the numerical aperture. Or it's larger than that, excuse me. It's larger than that, so we can tell them apart. But if the spacing is larger than that in the image plane, then, and that should be divided by the magnification. No, yeah, that should be divided by the magnification. My bad. We were focusing, we're taking a distant object and focusing it. So the magnification would be less than 1 because this distance here is smaller than the object distance. This is what happens. This is what I'm used to writing on a board where I can immediately correct mistakes in the notes. Anyway, divided by the magnification. My bad. Anyway, over here, they're barely resolved because the spacing between the images is less than 0.6 lambda over the numerical aperture. And so the spacing between the objects would be less than that thing divided by some magnification, which might be, which is a number less than 1. All right, so this brings us to the concept of a point spread function. A point spread function just tells us how a point object's light spreads out in the image plane. We've got a point object, we've got a spread out image. And like we said before, the Gaussian is often a very good approximation, and we usually write out a Gaussian point spread function in this form, all right? We've got the intensity in the image plane equals some peak intensity at the center of the image multiplied by this function. And let's talk about the parameters. Before, I was writing e to the minus 0.27 times k squared times sine squared theta. Well, that's if it's diffraction limited. If we have a lot of aberrations in the lens, then it might not be diffraction limited, but it could still be spread out over some kind of roughly Gaussian shape. And that Gaussian shape will still have some kind of width. And whatever that width is, we put it here. And there's no guarantee that this image will be centered at the origin. If our object was off axis, then our image would be off axis. And if x or y or whatever we're using at the moment is our distance from the center, then we'd have to shift it by subtracting x naught or y naught or whatever from that coordinate. And so here we have a point spread function that is off center. And that might be a little bit easier to illustrate in a Mathematica file that I posted online. So here's what happens when we play with x naught. As we play with x naught, if x naught is negative, then it's centered at negative values of x, because up here we see that it's a function of x minus x naught. And x minus x naught is 0 when x equals x naught, so our exponent is 0, which gives us the largest possible value of this function. The width, w, if I make w large, well then I have to go pretty far from x naught before this exponent has changed a lot. So if I make w large, I make the width large because I have to go really far from x naught before I can make a big change in the exponent. If w is small, the width is small, and then there's an amplitude, sometimes called a, sometimes called I naught. Now, if I have many point objects, then the intensity that I detect in my image plane will just be a sum over all of the objects of a bunch of point spread functions. And each point spread function will be multiplied by possibly a different value of I naught. It could be that one of our point objects is brighter than another point object. And it could be, or probably will be, that each point object is at a different position. So each x naught value is going to be different. So I'm going to have x naught j indicating the center position of object j. And usually W won't differ for the objects. There are exceptions. One, of course, would be if the different objects are emitting different wavelengths of light, that would affect the width. There are some tricks that I'll show you a little bit later where how far out of focus it is, how far the object is from the focal plane of the lens will actually change the shape of the image. The defocus doesn't just simply blur things out uniformly, but they put special kinds of interference filters in there so that defocus qualitatively changes the shape. Those are unusual cases. Those are not the norm. So for our purposes for now, W will just be a property of the lens. If we go to 2D, then each object will have associated with it an x0j and a y0j. It'll have two coordinates associated with it. And instead of having e to the minus x0 squared, you're going to have something like this. Basically, you could think of the images as being off-center circles. And sometimes the point spread function won't be a Gaussian. If it's not a Gaussian, then we replace e to the minus x squared with some arbitrary function. Many textbooks call it h of xy. I think that's just a notation that got carried over from the signal processing literature and engineering. I know one author who calls it q of xy. Sometimes the point spread function is not circular. And if it's not circular, then you would write it as h of x minus xj, x0j, y minus y0j. Let me show you an example, a pretty important example, where it's not circular, where people use elliptical images. So one of the easiest ways to do three-dimensional imaging, I think I mentioned this to you several weeks ago when talking about aberrations, was you take this really expensive microscope objective and you get a reasonably well-designed tube lens over here. And then in between those, you put some cheap off-the-shelf cylindrical lens. And that cheap off-the-shelf cylindrical lens, what it does is if you set things up right, you still get a circular image when everything is in focus. It might shift the focus, it might slightly widen that circle, but you're still a special distance where if the object was at that special focal distance, you get a circular image. If you're a little bit above that plane, you get a horizontal ellipse the way they set it up. And if you're further above that plane, you get an even wider horizontal ellipse. If you're below that plane, if your object is below that plane, your image comes out as a vertical ellipse. And if you're even further from that plane, it's an even more distorted vertical ellipse. This is, as far as I can tell, the cheapest way to change your microscope from doing 2D to 3D imaging. It's not necessarily the best. There are people who do these really elaborate interference filters where if it's in the plane, maybe it'll be a circle. And if it's out of the plane, it'll be some very weird distinctive shape. And how that distinctive shape changes will depend on how far out of focus. Other people will do a point spread function that's never circular. It's some weird shape. And as you move in or out of focus, the shape rotates. And so how much it's rotated tells you the z coordinate. But whatever they do, however they set it up, we could still just say we've got a point spread function there. The details don't matter for these purposes. Could be the most elaborate helical rotated shape around, but we've got some point spread function. And the inputs to the point spread function will be x minus xj and y minus yj, where xj and yj are, or x0j and y0j, depending on your notation, are the center coordinates of your point source. Any questions? All right, so what if we have an extended object? A lot of the objects I deal with in microscopy are point objects. We just look at individual fluorescent molecules, but that's not always the case. Well, if you have an extended object, we're just adding up a whole bunch of point spread functions, one from each point on the object. And if you add up an infinite number of things separated by infinitesimal distances, then that's an integral. So you're integrating a density. This is a density of sources or a brightness of sources. Like here, it would just be 0 or 1. But if this part of the object were brighter than that part of the object, then this rho function here, this density, would have a larger value here than there, or vice versa, depending on the brightness distribution. So you got a density of sources. That's just telling you, do I have a source here or not? If so, how bright is it? Well, if I've got a source there, take the brightness of that source, multiply it by a point spread function, and this is the coordinate of a point in the image plane, and this is a coordinate of a point in the object plane. So we're in the image plane at height y. We're looking at something down here. And so because this y and this y, or this y and this y prime are not the same, we're getting a point spread function that was shifted, all right? If I were exactly, let's say here and here, this is the image point corresponding to the edge of the object. The signal I get here due to this point is just the center of the point spread function. But what if I were here? Okay, now this point, of course, corresponds to some other point in the object. But I'm here, and I'm trying to figure out how much light do I get here because of an object here. And if the point spread function were just a point, well, the answer would be 0. But we know that light spreads out. And because light spreads out, the light I get here, yes, it depends first and foremost on the object here, the object whose image is centered here, but it also depends a little bit on the object here, because the light from the object here, it didn't all go to this image point. Some of it's spread out. And so I get a contribution that's equal to the tail of the point spread function. So at each image point, I'm adding up the point spread functions from all of the object points. And if that image point is really close to where geometrical optics says your image point would be, then I get a very large contribution from that object. If I'm far away from that, well, I get a very small contribution, just the tail of the point spread function. So here's another illustration of it. y1 prime, y2 prime. Here's the image point corresponding to y2 prime. Here's the image point corresponding to y1 prime. And over here, of course, I get the point spread function due to object 1. It's a big contribution. I'm also getting a little bit of the light from object 2. Not a lot, but a little bit. All right? So that's why I'm integrating this point spread function. That's why I'm adding up all of those contributions. All right, so the detected intensity is the integral of rho of y prime, point spread function shifted. And this kind of product integral, this is a very special product integral. It's called a convolution integral. The convolution integral is not just any old product of functions. If I had rho of y prime, ps of y prime, psf of y prime, that would be something else. That would not be a convolution integral. But I'm integrating over a variable y prime. One of the functions in my integrand is evaluated at y prime. The other function in my integrand is evaluated at y minus y prime. This is a special integral. It's called a convolution integral. I motivated it by setting up a situation with point spread functions. Things like this show up a lot in signal processing and in imaging. And so because they show up all the time, mathematicians have spent a lot of time studying them, and that's why they have a name for this kind of integral, because it shows up all the time. Convolution integrals have a lot of interesting mathematical properties. For starters, we could swap around the way we evaluated the functions, and it would still work, still get the same result. By the way, we can even do this convolution with point objects. You may be thinking, well, with point objects, we're doing a summation, not an integral. Well, this is part of the great physicist-mathematician cultural divide. If you're a physicist, then you believe in the existence of a function called the delta function. The delta function is a function that is zero everywhere, except when its input is zero, in which case the delta function is equal to infinity. So delta of y minus y naught is zero everywhere, except when y minus y naught is zero, and then it's infinity. And the integral of the delta function is 1. And if you're a physicist, you believe in this. If you're a math major, you don't believe in this, but you do believe that mathematicians worked out the theory of something called distributions, which are not probability distributions, so they're related to that. You believe that mathematicians worked out the theory of something very close, and the limiting behavior of this thing that is very close is the delta function. But we are simple physicists. We are not skeptical mathematicians, so we shall merely accept the existence of the delta function. If you really want to make a math major cry, you just start talking about delta functions. It makes them cry. My physics professors, we had a lot of math majors taking physics classes with us, and my professors enjoyed torturing the math majors that way. So if you need a physical picture of a delta function, think of a series of Gaussians getting ever narrower. Here's a really wide Gaussian. Here's a narrower Gaussian, so it gets smaller at most points, but larger here. Here's an even narrower Gaussian, and we could just keep making our Gaussians narrower. They would decrease, tending towards zero everywhere out here, and tend towards infinity there. And the areas under those Gaussians would all be the same. So here's the nice thing. If I integrate a delta function multiplied by a PSF, this is only non-zero if y prime equals y naught. Y prime equals the position of the object. So what I do is I plug in y prime equals y naught here, because this PSF, yeah, okay, it's not PSF of y minus y naught everywhere. It's not equal to that for all values of y prime, but it's equal to that at one value of y prime. It's equal to that at the only value of y prime where the delta function is non-zero. So if I take this delta function, multiply it by the PSF, and integrate, I get out the PSF evaluated at y minus y naught, which is what I would be adding up if we weren't doing convolution integrals. We were just simply adding up a handful of point spread functions like I did there and there, or there.
Good question, Professor.
Yeah.
What is the purpose of having the y in the point spread function?
Y is where you're actually calculating the light intensity. I'm calculating the light intensity at this point y. The value, the amount of light that I'm going to get depends on how far y is from y naught, the position of the object or the corresponding image point. So if y is right on top of the image point, then I'm evaluating the PSF at 0, the center of the PSF, which is really bright. If the image point is really far from where the object is, or the point in the image plane corresponding to the object, then I'm getting something very faint. Make sense?
I see. Thank you.
You're welcome. Okay, so here is, let's look at one more illustration of adding up point spread functions. Another way to see that is I've got 2 point spread functions. And I've got 2 point objects that are separated by some distance that I can play with. And the intensity of the second object is something that I can play with. So I've got one object whose image forms at 0. And it's spread out like that. I've got a second object whose coordinate I can play with. All right. And the light intensity, say here, the combined image, which is what our camera actually detects. Our camera doesn't detect this blue curve and this orange curve. The camera just detects the combined image. That's going to be the sum of this, right here, it's going to be the sum of this orange point spread function and this blue point spread function. We add those two up. And this contribution, the contribution from the orange thing, depends on how far I am from the center of this image. The contribution from the blue thing depends on how far I am from the center of that image. So maybe that helps clarify it. And then you can also see here that if they're really far apart, okay, in principle, at this point here, I'm adding up 2 point spread functions. But one of those numbers is big, it's like probably 0.7 or so. And the other number is minuscule, it's 10 to the minus a big number. So in there we could ignore the fact that this is a convolution. But then here we start to see, when they're this close together, we see that actually the combined image is distinguishable from the two individual point spread functions. You know, if they're this far apart, you can't tell any difference between the two individual point spread functions and the combined image. Over here, you can definitely tell a difference between the two individual point spread functions and the combined image. And so like at this point, you're adding up the orange contribution, which is large, and the blue contribution, which is small but not negligible. And here you're adding up equal contributions from the two. And here you're adding up now a larger blue contribution and a smaller orange contribution. Make sense?
Yep.
Okay. All right, so here's why it's really important that this is a convolution integral. Convolution integrals work very naturally with Fourier transforms. At some point in math methods, you have seen or will see that you can take functions, multiply them by exponentials, complex exponentials, and get something out. You could take a function I of y, the intensity of the image, multiply it by e to the minus I ky, integrate, and you'd get out a Fourier transform. And then you could take that Fourier transform and reintegrate it and get back the image. Now, the reason why you would want to do that is not just so that we can do two integrals and get back what we started with. That would be a rather tedious exercise. It's that we can think of this image as being the sum of many different sine waves. And we care about that because, well, often in images, the noise is at a very high frequency, because a lot of the noise in an image is just varying from one pixel to the next. Each pixel, besides having however much light came from the object, there's going to be some electronic noise in there. Each pixel's electronics are roughly independent of the other one. So the signal on each pixel is a combination of what you want to see, the light, plus some random electronic noise. And so the noise is very high frequency. It's something that varies a whole lot from one pixel to the next. Whereas the signal is usually smooth. If your image isn't choppy, then your signal had better be smooth. Your signal had better not change much from one pixel to the next. Because if it is changing a lot from one pixel to the next, it's choppy. If it's not changing much from one pixel to the next, it's smooth. So this is a way of thinking about signal and noise in an image. The high frequencies, which when we're working with sinusoidal functions, it's going to be 2 pi over 2 times the pixel size. It's 2 times the pixel size because anything that fluctuates from one pixel to the next must vary on a scale of 2 pixels. You could think of it as being made up from sine waves whose wavelengths were 2 pixels or sometimes 3 or 4 pixels. So 2 pi over a few pixel sizes. Another way to see that is, I'm going to go into a program called ImageJ, which we don't use much in here. I didn't make you download it or learn it, but it's a free package made available by the National Institutes of Health. NIH, it's a federal agency that sponsors medical research. The difference between NIH and CDC is, it may seem like a fuzzy one because right now the most famous person at NIH is Dr. Fauci, the head of the National Institute of Allergies and Infectious Diseases. And the reason why people study allergies and infections in the same place is because the immune system fights infection, and when the immune system fights the wrong thing, it's called an allergy. Anyway, NIH mostly funds research. They are mostly a research agency, not an action agency. Although NIH does have experts who do respond to crises and do advise the government, the most famous one being Dr. Fauci right now. CDC does have researchers, but CDC also has a whole lot of people who, rather than staying in the lab, will go to wherever an outbreak is and start building hospital tents and start taking over hospitals or advising the people who run hospitals on what to do about a disease that isn't particularly common. They have people, the point is that CDC has people who go into the field and take action. And they also have people in the lab. NIH does have people who go into the field and take action, but mostly they have people in the lab. And so their people in the lab help the people who are in the field taking action. I mean, right now, all of these specimens that CDC is collecting, there are people who are compiling the RNA sequences of all those viral specimens and constructing phylogenetic trees. There are to monitor the evolution of the virus and understand it. There are people at NIH who are doing vaccine research. There are people at NIH who are doing research for antibody tests. But on a day-to-day basis, NIH does more long-term research and is more likely to be funding basic research in a university. I mean, it's entirely possible that someday NIH, I might succeed in getting an NIH grant to do some basic optics research that's applied to biology, whereas the only way I would get a CDC grant is if I proposed to do some research that was directly, immediately relevant to something that they think they're going to need in the near term. Anyway, because NIH is a research institution, they make a lot of free research tools available. One of those is called ImageJ. It's an image processing program. Here I've got a nice picture that I just pulled off the internet. And I was going to try to expand that window. Okay, if I expand it, you can see that it is a little bit choppy because I made the pixels really large. Now, let's do something called FFT processing. We're going to take the Fourier transform. So we're going to break it up. We're not going to, well, let's actually just do the FFT first, okay? So here's the Fourier transform. It doesn't look like much, but each intensity, each pixel brightness in here corresponds to a different frequency. And why that was not what I expected. Okay, that's weird. Let me reload that image. Okay, let's try that one more time. Because before I was Fourier transforming a very small region. This doesn't look like much, but this is telling you how bright each of the sine waves would be. These are positive frequencies. Here the X and Y spatial frequencies are positive. Here the X spatial frequencies are negative and the Y spatial frequencies are positive. Here both spatial frequencies are negative, etc. Doesn't look like much. That's not how the human eye thinks about things. But if I were to cut off the really high frequencies, let's do that. Let's cut off the really high frequencies. So I'm going to do something called a band pass filter. And I told it to, you have to tell it which large structures to get rid of. So I'm going to tell it to only get rid of large structures that are larger than the image. That way it will ignore me. I'm going to tell it to get rid of structures with spatial frequencies so high that they're 2 pi over 4 pixels or larger. You see how that image just got blurry? That means that I didn't just remove noise when I got rid of the really high frequencies. I also got rid of signal. Getting rid of high, when we lose signal, and when we remove high frequencies and lose signal, that means that we had a really good image. That means we had an image where the signal to noise ratio was good, that even those high spatial frequencies were telling us something, that we lose information. You may be thinking, how do we quantify that? We'll take an image processing class. But the human brain knows that you lose information because you look at it and there are things that you can't see. Let's undo that. Let's look at the filter that we used for that. Bandpass filter. Let's have it display the filter. And let's, here it only looks slightly blurry because I told it what, I tightened the criteria. We didn't get rid of as many spatial frequencies. And this is basically saying that it kept all of the low spatial frequencies. And as we went on to higher spatial frequencies, it multiplied the low spatial frequencies by 1, white. It multiplied the slightly lower spatial frequencies by a light shade of gray close to 1. It multiplied the middle spatial frequencies by a middle shade of gray, 1/2. And then it multiplied the higher spatial frequencies by darker shades of gray, numbers closer to 0. That's what bandpass filtering is. Questions?
Can we see the image when you only filter out low spatial frequencies?
Sure. Let me first undo the filter. And then let's get rid of the low spatial frequencies. So we're going to do a bandpass filter. I'm going to tell it to filter large structures down to, let's say, 3. This is a 500 by 364 image. So let's tell it to filter large structures down to 300 pixels. And let's filter small structures up to 0 filters. So 1/0 is infinity, so it's going to keep all of the high spatial frequencies. That wasn't a stringent enough filter. Let's undo that process and let's try it again. Custom, oops, I didn't want custom filter. FFT bandpass filter. So let's go to 100. You see what just happened? Do you see how the color changed down here?
Yeah.
Let's do an even more, well, let's undo it and then redo it. Let's filter the large structures down to 25 pixels. Okay. You see how a whole lot of noisy things are coming out and the background looks weird and there's this dark shadowing here? What we're essentially doing is we're filtering out the really low frequencies here. We're only keeping the fine details. So a lot of the background becomes weird. Here in the wood grain, all of the noise and variation in the wood grain is showing up because we're no longer adding a background to it. Let's go even more radical. This will tell you, the fact that we have to go this far will tell you exactly which frequencies matter. We're still only seeing subtle effects. So let's go down to 10 pixels. Okay, so we're keeping a whole lot of high frequencies still. All right, we've completely changed the background there, but the details haven't changed. All of the carving on the pumpkin is still visible. All of the, not the pumpkin, the watermelon, all the carving on the watermelon is still visible. All of the background, though, the large areas now look like weird colors, these weird hues in here. Other questions? All right, so that's the significance of the Fourier transform of an image. When you play around with the spatial frequencies, you can change details versus background, and that's why people in image processing care a whole lot about, that's why people in image processing care a whole lot about the Fourier transform of an image. And by the way, some of the, this is something that carries across many areas of science. Remember the Event Horizon Telescope, the people who took a picture of a black hole last year? Well, for a variety of reasons, there was a bunch of news coverage around a couple of scientists who one of them who mostly worked on the image processing. She's a computer science professor at Caltech now. And I'm highlighting her partly because the news highlighted her for unrelated reasons, but partly because her real expertise is not astrophysics. Her real expertise is image processing. And if you look at her CV and you look at her research interests, she is actually very versatile in image processing. And I bring that up not to disparage her astrophysics knowledge, but to point out that in a lot of these big research collaborations, the techniques that are actually going to spill outside have much less to do with the physics itself than with the computational tools developed for it. So her real expertise is image processing, and she's going to work on that in many fields besides astrophysics. And frankly, some of the techniques that she developed for imaging a black hole with a radio telescope, I think could be applied to biomedical imaging. Put it in another context, the biggest contribution what is the biggest contribution that CERN, the big particle accelerator in Europe, has made to human civilization? The World Wide Web. Not to disparage the discovery of the Higgs boson or the ongoing search for physics beyond the standard model or the validation of so many other predictions within the standard model, but CERN has always been a place where people not just do physics, but they develop tools for analyzing and sharing very large quantities of data. And so the biggest spillover from CERN has been the World Wide Web, originally invented to share data at CERN. Likewise, a lot of things done in astrophysics, not to disparage any of the individuals as astrophysicists or their scientific acumen, but the real spillover for the world has been the signal processing and the image processing. I have no idea if anything discovered in space with adaptive optics will change our lives, but I know that adaptive optics is enabling very exciting work in neuroscience to look through thick tissue. Okay, so Fourier transforms matter. Now, a basic fact, okay, we want to Fourier transform the image. And the image is a combination of two things. It's a convolution of the object with the point spread function. So the Fourier transform of the image will be the Fourier transform of this convolution. So we're taking a double integral over y, all the points in the image, and each point in the image is an integral over y prime, all the points in the object. We're multiplying three functions. That looks like something hopelessly convoluted, no pun intended. But it turns out that a basic fact of Fourier transforms is that if you Fourier transform one of these elaborate convolution integrals, you get the Fourier transform of one of the integrands multiplied by the Fourier transform of the other integrand. So you get the Fourier transform of the object multiplied by the Fourier transform of the PSF. And the point spread function decays, all right? It can't go any farther than 2 pi over lambda. Once we get up to frequencies above 2 pi over lambda, it can't see anything smaller. So there is a cutoff, but oftentimes the cutoff is even lower than that because of aberrations, because aberrations blur the image out even more than the diffraction would. So the PSF is removing high frequency information. We take this point spread function, which goes to 0 by the time you get out to 2 pi over the wavelength. We multiply it by the Fourier transform of the object. And even if the object's Fourier transform has very high spatial frequency components in it, we're not going to get anything in that image with those high frequency components. You could also think of it in terms of the blurring process. Say we've got something with width W, all right? Well, it gets blurred out because the light from this point will not form another sharp point in the image. It'll form a blur that spreads out like that. And the light from this point will not form a sharp point in the image. It'll form a blur that spreads out like that. So square waves, nice sharp objects, become blurry when you convolve with the point spread function. So there's a special name for the Fourier transform of this point spread function. It's called the modulation transfer function, or MTF, to correspond with PSF. And that modulation transfer function is just the ratio of the image's Fourier transform to the object's Fourier transform. So it's how bright is this high frequency thing in the image relative to the high frequency thing in the object. And since Fourier transforms, since point spread Fourier transforms decay, they go to 0 at high frequencies, the modulation transfer function decays. No matter how big this amplitude, no matter how big this high frequency component might be in the object, in the image it's going to be small because all the high frequency things in the point spread function are small. Here's another way to interpret that. Take a nice sawtooth. Say that the width of the peaks is W and the spacing is W. So the number of lines per millimeter would be 1 over 2W. Or if we work in the more conventional notation, 2 pi over 2W would be K, spatial frequency. Well, our image gets blurred out. So instead of seeing a nice sawtooth, we see something roughly sinusoidal. And that will be 1/2 plus the modulation transfer function over 2 multiplied by this cosine or sine depending on the phase. So the modulation transfer function is the maximum intensity minus the minimum over the maximum intensity plus the minimum intensity. And so you could measure a modulation transfer function by taking some object that you know to be a sawtooth, and then image it. And and if the sawtooth is really fine, you're gonna get out a blur, all right? And you could look and see what are the peak and minimum intensities in that varying blur. You could take the difference between maximum and minimum over the sum of maximum and minimum and compute a modulation transfer function that way. And people often talk about that rather than spot size because that's the language used by people who work every day in imaging. They don't tend to talk about spot size. They tend to talk about spatial frequency, either K 2 pi over the line spacing or just 1 over the line spacing, which would be the lines per millimeter. Any questions so far?
Yeah, but when we're trying to find point spread functions, is that just like, do we find that empirically for each lens?
Could you say that again? I couldn't hear you the first time.
When we're trying to figure out a point spread function, do we just have to do that empirically for each lens that we have?
Yeah, so you either do it with Zmax or you just measure a point spread function. You just take something that you know to be much smaller than the wavelength of light, and then you get an image of it, and then you can Fourier transform that and get a modulation transfer function. And people do similar things to modulation transfer function, to point spread functions. It's not just something that you do with visible light. You would have a point spread function for infrared light. If you were doing microwave or radio imaging with antennas, you could come up with an analogous point spread function for that. A radio telescope most definitely has a point spread function. I'm not sure what language they use for it. They probably have different terminology because the radio telescope community has more in common with electrical engineers doing radio communication, but there are analogous concepts throughout the field. I know that there are image processing tools developed in radio telescopes that were later used in light microscopy. Anyway, the largest spatial frequency that you could see would be roughly 1/2 times the PSF width, because if this were comparable to your PSF width, then you would basically have a blurred out point spread function here, a little gap, then a blurred out point spread function there. So your peak spatial frequency, the cutoff spatial frequency, would be roughly 1/2 times the spot size. And if your spot size in the diffraction limited regime is 1/, the aperture, then your frequency cutoff should be 1/, that spot size, or 1/1/, the aperture, or the aperture. So this leads to the surprisingly intuitive concept that the wider your aperture, the greater your bandwidth, meaning that a wide aperture lets you see more spatial frequencies, and the number of spatial frequencies you can see is just directly proportional to the width if you're diffraction limited. Now, if you're aberration limited, well, your spot size is proportional to the cube of your aperture size. So the largest frequency that you have any chance of seeing is going to be proportional to 1/, the spot size, or proportional to 1/, the aperture cubed. So your cutoff frequency versus aperture, for small apertures, it's growing linearly. You're diffraction limited. At large frequency, it's decaying as 1/, aperture cubed. You're aberration limited. And so you want to work around here. You want to work near the maximum, the largest possible cutoff frequency, which happens at that transition from diffraction limited to aberration limited. And that's part of the reason why the human eye is diffraction limited during the day when your pupil is very narrow, and it's aberration limited at night when your pupil is very large. And so around dusk, halfway in between, you're going to be right at that transition from diffraction limited to aberration limited. So in sort of the middle case, you are working at the maximum cutoff frequency. And of course, it's interesting to note that a lot of predatory animals are most active around dusk. So it was necessary for us to have our best eye, or our ancestors who lived much closer to predatory animals than we do, to have their optimal eyesight around dusk. And finally, here's a typical shape of a modulation transfer function. By convention, people will often ask, okay, when has it decayed to 1/2 of its maximum value? That will tell you roughly what the cutoff is. I mean, you can say, well, technically it's not completely cut off. Even out here you can see something. Yeah, but it's not very useful. So 1/2 of the maximum is a good heuristic. And again, if you really go far into signal processing, you'll be able to get much more quantitatively precise about what it means to have such and such amplitude at such and such frequency. But a good estimate is that if you're at 1/2 of the peak, then that's about as far as you can go and still have anything that stands out relative to the stuff at the peak. As you go further out, it's going to be weak, not just in absolute terms, but particularly in relative terms, relative to what you are seeing here. Any questions before we go to Zmax? All right, well, Zmax is perfectly capable of computing, modulation transfer functions because it's perfectly capable of computing point spread functions. And so what I did was I took sort of a deliberately bad imaging situation. This achromatic doublet was really set up to take parallel rays from infinity and focus them. Well, I had it do the opposite here. And we could look at the spot diagrams. And we've got the aperture pretty narrow here. And when the aperture is pretty narrow, what we see is that our spot diagrams are much smaller than the airy disk. If we look at our modulation transfer function, it decays roughly like the shapes we've been looking at. And for all of the colors and all of the planes, let's talk about what sagittal and tangential mean. This is the tangential direction, okay? If we've got an off-axis object that's down along the y-axis, in the image plane, tangential would mean going towards or away from the optic axis. The tangential direction would be along that line between the image point and the optic axis. The sagittal direction would be the direction out of the screen, okay? It would be looking at how much things vary when you go out of the screen. If instead of modulating, instead of having an image with features that were in this direction, up and down, we had features going in or out of the screen, what would it look like? You may be thinking, well, shouldn't the modulation transfer function be the same? Well, on axis it should be, because on axis the image is circular, but off axis it's got very substantial coma aberration. And so you may be tempted to think, hey, I've got a very narrow spot size in this tangential, the sagittal direction. So if I got a great spot size in the sagittal direction, then I should have a great point spread function in the sagittal direction. But keep in mind that this is diffraction limited, all right? So you're not seeing much of that. Now let's see what happens to our modulation transfer function if we make the aperture narrower. We're in the diffraction limited regime. So if I'm in the diffraction limited regime and I make my aperture narrower, what should happen to the spot size? Increase or decrease? Should decrease. Sorry, it should increase. Should increase. Because a narrow aperture produces a lot of diffraction. All right, and what you see is that the shape of the modulation transfer function didn't change, but all of the spatial frequencies on this axis got smaller. Let's redo that. I'm going to go from 2.5 to 5. I'm going to double my aperture. So now the spot size should get cut in half. And you see that before it decayed to half, a little bit below 7.5 lines per millimeter. Now it decays to half, a little bit below 15 lines per millimeter. All right, which means that the frequency where the modulation transfer function has cut by half, that frequency has doubled. So because we've gone to a larger aperture, we have a smaller spot size. We are able to get higher spatial frequencies out. Now, let's see what happens when we double the aperture again. Okay, well now all of a sudden everything starts to look weird. And if we look at our spot diagrams, we see that everything is now larger than the airy disk, okay, which means that we are aberration limited. All right, further proof that we're aberration limited. Can you think of something we could look at that would immediately compare the beam profile with the ideal diffraction limited case, something we could do in some kind of analysis we could do? Let's look at enclosed energy. And you see how in our enclosed energy graph, it's showing the diffraction limit in black. Now you might say, well, maybe we just need to do a quick focus. Let's do a quick focus. Helps a little bit, not much, okay? We are definitely aberration limited because the way the energy is spread out is substantially different from the diffraction limited case. Whereas when we were at that very small aperture, everything was pretty much exactly matching the diffraction limited case. And even at that intermediate aperture. So let's go and see what this has done to our modulation transfer function. Our modulation transfer function, well, we went to the aberration limited case, but we must be pretty close. We find that what we find is that for some cases, we are actually getting much worse than we had before. For some cases, you might say, hey, it's better than before. Look, we're able to go out to higher spatial frequencies. But we're going out to those higher spatial frequencies because if you look at our spot diagram, with this coma aberration, we're getting a very narrow, not narrow is the wrong word, we're getting a very asymmetric point spread function, all right? And so this asymmetric point spread function, yes, it means that our point spread function is narrow in some directions, but everything is so warped that I wouldn't call that good. I would say that you should take your worst modulation transfer function and go with that, because the quote-unquote best modulation transfer functions that you're getting out here, those best cases are really just for one direction in some very far off axis points. So some of your very far off axis points have gotten warped in such a way that some of the directions are going to look good and some of them are going to look bad, but you're not going to get even image quality. Questions? So your next ZMAX assignment, the last ZMAX assignment before the final exam, will be to basically set up an optimized lens for one-to-one imaging. One-to-one imaging is quite common for things like scanners and photocopiers. So I want you to do one-to-one imaging, set up an optimized triplet of lenses, and the assignment kind of gives you an example of an optimized triplet of lenses. And then look at the modulation transfer function of that optimized triplet and identify the diffraction limited and aberration limited regimes. Any questions?
So when we're looking at that plot, the modulation transfer function plot that you're just showing us, the sagittal and tangential, we were saying, are like different directions. So like ideally we would want those to be similar, right?
Yeah, they're going to be similar if your spot diagram is roughly circular. But if you have coma aberration or astigmatism, then they will be different from each other. And so a modulation transfer function that's different in the tangential and sagittal directions is basically telling you that you have some pretty bad coma and or astigmatism. And it can look really good because you're like, hey, in one of these directions it's really narrow. Yeah, because you've got astigmatism and coma. Other questions? Well, then what I would suggest you do right now is I will stay logged in, and you should start working on reading the next assignment and trying to see what you can do to optimize that triplet. Once you've got the triplet optimized, making the modulation transfer functions and reading them off will be pretty straightforward. You're going to want to always look at the worst modulation transfer function, not the best. Because the best is just an artifact of aberrations. The worst is what is limiting you. And I'll stay logged in for those who want to work in ZMask and ask questions. I know there were also a few people who wanted to ask questions about some other science-related topics after class. I'm happy to take those questions as well.